My name is Connor McShaffrey. I'm going to be giving you a quick overview of some work that I've been doing with Professor Randall Beer at Indiana University on decomposing the viability space of agents. So, broadly speaking, the goal is that if we imagine that we have a dynamical system describing an agent, we want to be able to predict which initial conditions of that agent environment system are going to lead to survival versus which are going to lead to the system perishing. And a good chunk of this is going to be building off of work that I showed at A-Life last year. So that paper is already out. Broadly speaking, you can imagine that our agent can exist within this domain of viability shown in blue, which has a boundary to it. And there's a complement to that region, which is where no agent is possible. We then have dynamics within that viability region that can either lead to something like a homeostatic regime in green, or will lead to a terminal trajectory where the agent is going to violate one of those physiological boundaries. The goal is to be able to identify organizing principles that let us say all of these initial conditions in green are going to result in a homeostatic regime between the agent and its environment. And all the points in this transiently viable region are going to perish in some finite time. So the way that I'm going to show this to you to start is with a two-dimensional protocell model where there's two metabolites and two food molecules. And these lollipop-looking arrows represent there's an interdependency. So you can't synthesize molecule 1 without molecule 2 and vice versa. And both metabolites decay into inconsequential waste products. We then give a simple viability boundary that says if either metabolite drops beneath the value of 0.1, you die from decay. If their sum exceeds, 20, then you get bursting from osmotic pressure. So just a really simple toy example to see whether these principles are possible to derive. Now, the first thing we can do is sample the space for different trajectories. So what I did here is I took 1 million initial conditions. I numerically integrated each initial condition for a duration of 800. And then I recorded the normalized amount of time it was alive for that duration. So what you see is that there's two dim regions. The top one is a little bit hard to see on the projector, but there's two dim regions where survival took place, but for less than the tested duration. And then there's one really bright region where it survived the whole amount of time. And then we see a dark region where life never happened. Those initial conditions terminated immediately. So this is what we're going to try to understand. The first thing we can do is that we can just impose the viability constraints. That's kind of a trivial step, but that separates the regions where we had a positive survival score from where there was none. The next thing we can do is look at some trajectories to get a feeling for what dynamics are happening in the space. So we see that here in orange, trajectories in this region are violating the lower viability constraints. And then we have in that middle part here, they seem to be converging to the right. And in the top region, they pass over that diagonal viability constraint. We can start to explain this by doing a phase portrait analysis where we identify stable attractors within the system. So here we have two attractors shown in dark blue. We can see that one of them explains this transiently viable region because all initial conditions on this side of the basin of attraction are going to tend to converge to that point. So they're going to die in finite time. We can see why these are all surviving because they're converging to an attractor within the viability region. But something's left unexplained. We have that whole transiently viable region up there. That is, if we expand these trajectories, if this didn't result in death, they would be within that basin of attraction. So that's a problem. We're missing a manifold. One way we can get around this is to take a step back from this global behavior and think about what can happen at the boundary between life and death. So here we have our viable region, our terminal region. One possibility is that you die if you're at the boundary. It's kind of sad. Another possibility is that you recover, you move back into the boundary. And if you're smoothly varying from a terminal vector to a recovery vector along a boundary, you can have a point of tangency. And that locally separates instantaneous death from instantaneous recovery. If we go back to our protozoa model and look at the vector field along the boundary, we see that there's 3 points of tangency separating vectors that result in immediate recovery versus immediate death, but some of them are in transiently viable regions and some are in our asymptotically viable region. But it ends up that if we focus on this one right here, which remains asymptotically viable in its forward time trajectory, and we look at where it came from, we get what we call a mortality manifold. And what that does is that if we have a basin of attraction that is not fully contained within the bounds of viability, such that you have transiently viable trajectories and asymptotically viable ones, this structure separates those outcomes. Now, one of the pieces of feedback I got on this is when I presented last is, oh, well, Connor, that's all nice and good, but that's a 2-dimensional model. And we don't know how useful that is as an example. So we won't have time to go through it, but I'm going to show you a 3-dimensional model, just because that's as high as we can go in a 10-minute talk while still being able to wrap our heads around what's happening. So we're going to take our same cell, but we're going to put it in an environment, and we're going to give it the ability to chemotax. So now we have a dynamical system where we've added in this X dimension, where depending on where it is in X, it gets different amounts of the 2 food molecules. And if we think about the geometry of our viability constraint, that means it kind of smears it out into this prism along X. And since this is a lightning talk, I'm not going to have time to show you the full derivation process, but I want to show you the end step. And I want to emphasize that the principles are very similar to what I showed you in the 2-dimensional case. And what you end up with is this graph, where it looks kind of gnarly, but basically what's happening is that this blue manifold is separating basins of attraction. This black line down here is an attractor of a kind that we won't get into the specifics of. And then we have a stable equilibrium point in the bounds of viability. The orange trajectories are the ones that violate a viability constraint, and the purple ones remain within it. And we see these magenta manifolds here. Those are mortality manifolds in 3-dimensional space. That's the same type of structure as this curve here. And the cool thing is that this analysis actually identifies this region down here, which is, it looks like it's basically flat against the viability boundary. But if you zoom in and sample trajectories, it's an additional mortality manifold within the system that separates transiently viable trajectories from those that will eventually reach that attractor where you end up in a homeostatic regime in the environment. And this is not just the metabolism at this point. This is a combination of the trajectory and the metabolic dimensions, and also the chemical fields that the cell is moving in. I didn't get a chance to talk about it here, but also in the paper, I talk about how you can generalize the idea of bifurcations to these systems. So you can think about parameter changes and how that impacts the survival landscape. And this is really important because a lot of models in artificial life and computational biology have physiological constraints in them. But generally, there's not a ton of work on organizing principles for those things. I also want to quickly plug that we have 2 papers coming out from this conference, one of which takes the framework I just showed you and generalizes it to multi-agent systems. So if you like agent-based models, that might be of interest, where you can do the same thing. You have a space of multiple interacting agents, so you can decompose it into transiently and asymptotically viable. And then also the paper that I worked on with Professor Beer and our undergrad Tom Gall, which was presented on this morning on deriving intrinsic viability constraints in cellular automata. So, and I have 15 seconds left in my 10 minutes, so I feel like I timed that decently well. Oh, and then thank you. Last 15 seconds is for thank you to both the people that supported me in tangible ways and in the NSF that threw money at me.